So we're here to solve a few problems from the chapter Motion in One Dimension. Before we start with the problems, one of the common ideas is that this chapter is not very important because not many problems come and all this stuff. If you look at it technically, only about 2 to 3 problems come in JEE Main and no direct problems come in JEE Advanced. But the truth is, a lot of indirect problems come from this chapter, both in JEE Main and JEE Advanced. And also, a good understanding of this chapter and of these problems is important to solve higher level problems in other chapters like motion in 2 dimension, Newton's laws, and other mechanics related problems, right? So though people think it's not very important, it's actually very important. Okay, so let's quickly start with the problems. Now, what is the first one say? All right, let's quickly write down what information we have from the first problem. So we have m is equal to 10 power minus 2, f of x, which is the force that's acting on it, is equal to minus k by 2 squared. What's important to note is that it varies with x, or it varies with the position. So the force varies with position, right? And k is a constant, which is equal to 10 power minus 2. It's given to us that when t equals 0, x equals 1, and that's important. So at t equals 0, x equal to 1, v also equals 0. And what we need to find is the speed of the particle, or the magnitude at x equals 0.5. All right, so we need to find the speed, which is nothing but the magnitude of the velocity at x equals 0.5, which means that we need an expression between velocity and position, right? That will help us. How will you find that? What is given to us is the force and the mass. So think about it. We know that F equals ma. So using this, we can find the acceleration. And if we find the acceleration, then using a equals v dv by dx, then we should be able to find an expression between velocity and position, right? So this is the thought process. Let's see if it works. So since F is this, we can directly write a is equal to F by m. This is from Newton's second law. This is equal to minus k by 2x squared into 10 power minus 2, because mass is given to be 10 power minus 2. It's important over here to note the units. Because it's in kgs, it's fine for us because kg is the SI unit, so it's simple. But if, for example, if the mass was given in grams, we would have to convert it to kgs. Okay. And from here, we know that k is equal to 10 power minus 2 Newton meter squared. So we can just directly substitute it because it's constant. So you get minus 10 power. Right. So this and this gets cancelled. We get minus 1 divided by 2x squared. So we're getting an expression over here where a is equal to minus 1 by 2x squared. So we're getting acceleration in terms of x, right? Now what do? As I said here, we can write acceleration as v dv by dx. A is equal to, I know, dv by dt, but this can be written as dv by into dx by dx. This as v dv by dx, because dx by dt, right? dx by dt is v. Yeah. Now again, why am I doing this? It's simple. As I said, our question demands a relationship between v and x, and therefore by making this simple shortcut, we get a equals v dv by dx. Okay. So v dv by dx equals minus 1 by 2x squared. Now what do? It's simple, right? We can cross multiply and integrate. So this becomes integral v dv we can bring dx to the other side, and now we can integrate it. Okay, but the thing is, this is not an indefinite integral. This is a definite integral with limits, right? Now if you look on the left hand side, we have v dv, or the variable that's changing is velocity here, and we know that velocity initially at t equals 0 is 0. So this becomes 0. And the final velocity we'll just say is v. Alright. Now on the right hand side, the changing variable is x, and at t equals 0, x equals 1. So this becomes 1. The final variable is x. So v basically varies from 0 to v and x varies from 1 to x. Now this is a place where people can make a mistake easily. It's very easy to just start with 0 and then directly say x varies from 0 to x. That's not true. So you should be careful over here and make sure your limits are correct. So now let's integrate. So integral v becomes v squared by 2, where this varies from 0 to v minus 1 by 2. This becomes v squared by 2 minus 0 equals So I'm going to leave it like this. So this is the final expression that we're getting, okay, in terms of v and x, right? Now, what do we have to find? We have to find the magnitude of velocity when x equals 0.5. Now, simple, we just substitute x equals 0.5 over here and then we find v, right? So this will become v squared by 2. If x is equal to 0.5 or x is equal to 1 by 2, so this basically becomes 2 minus 1, right? Which is equal to 1 by 2, correct? So v squared will finally be equal to 1, right? If we substitute x equals 0.5, which means that v is equal to plus or minus 1. Now the question says we have to find the speed, right? And speed needs to have a positive value. So the speed or the magnitude of velocity at that point will be equal to 1. And the answer is 1 meter per second. That's it. Okay, so once you read this problem, first of all, this is a single correct type of question, right? Which means that it has multiple options, out of which only one is correct. Now, the moment you read this problem, it might feel a little complicated, but it's actually simple. So let's try to draw a diagram and see if we can understand what's happening. All right, so let's say that this is your building of height h. Now what is happening is that an object A, let's say this is your object A, has been dropped, and once it has fallen through a height of x, another object of, let's say it starts somewhere over here, another object B is dropped at the same time. Okay, so once this reaches this point, let's call this point O. So when A reaches O, B is dropped. Okay, and what is also given is the height of B is this distance from the top of the building. This is y. Correct? Now what the question says is that once B is released, both of them reach the ground at the same time, or they take the same time to fall and reach the ground. Now how will you solve this problem? The first thing that we should note is that this is obviously a constant acceleration problem, because both these objects are falling, and we know that when objects fall, the acceleration is constant, right? So A is constant, and which means that we can use the simple equations of motion, right? The three simple equations of motion, because these are all constant acceleration over here. All right, now cool. What do we have to find? The options, if you look, they're all like relationships, so they're all equations between h, x and y, which means we need to find a relationship between h, x and y. How will we do that? It's fairly simple, because we can simply use the third law, the third equation of motion, and using that we can, I think, easily find a relationship. I'll tell you why. Because the third equation basically relates the distance traveled, displacement, and the time, right? S is equal to ut plus half at squared. So using that, we should be able to solve this problem. So let's see. So what is the first thing we need to figure out? We need to figure out what's the velocity of A when it reaches this point O, right? We need to find to input this all the variables in that formula. You need to find the speed or the velocity that A had when it reaches this point, because this is where we're comparing. We're comparing from here to here. What we know is that the time taken for A to travel from here to here is the same as the time taken for B to travel from here to here, right? So to analyze these two motions, or to analyze the second half of A's motion, we need to first figure out its speed when it reaches this point, when it reaches O. How will you do that? We can use v square equals u square plus 2as, right? So initially, let's say u is equal to 0. Let me write it down so it becomes simple. So when A is dropped, u equals 0, v is what we want to find, and s in this case is equal to x, correct? Because that's the distance it has been traveled. So v square equals right, A will just leave as A. We can of course change it to G. That doesn't really make much of a difference. S will become X because that is the distance traveled. So here one thing that you need to notice is I'm not paying much attention to the signs over here, because everything is happening in one direction. There is acceleration is in one direction. The displacement is also in one direction. There's no changes. So there's no, we don't, of course, see, it depends on the convention. We can say that, upward is positive, downward is negative, which means that A should technically be minus 9.8 meters per second squared, or A should be negative, so on and so forth. But since everything is happening in the same direction, right, because acceleration is also in the same direction and the displacement is also in the same direction, we don't really have to worry about the signs over here, which is, yeah. So therefore v squared equals 0 plus 2ax. Simple. So we get that so this v, right, this is the velocity that A has when it reaches the point O. Okay, when it reaches this point. That's fine. Now what do we do? Now we have to find the time taken for A to reach the ground from there, and then find the time taken for B to reach the ground from when it's dropped, and then equate both, because that's what we know. We know that the time taken for both is the same. So how do we do that? Let's first check for A. So for A, when it's traveling from O to the ground, right? From the point O to the ground. Over here now, how do you calculate the time? We know that S for this is equal to h minus x, right? Because that's different, because this distance is x and the total distance is h. So the overall distance that is traveling is h minus x, okay? U for this case, root of 2x, correct? Because that's the velocity it had when it reached that point. Cool. So using s equals ut plus half at squared, yeah. H right? So this is what we're getting over here, right? So this is the relationship between x and t. Now let's take B's case. Start with B over here. B has an initial velocity of 0 because it's being dropped, right? And what is the distance that it travels? That is s. The distance that it's traveling is from here to here. It's the total distance, and that will be equal to h minus y, correct? So we'll call this h minus y. So again, if you use s is equal to ut plus half at squared, now what do we do? So we have these two equations, correct? And what we know is this t and this t is the same. Yeah, because that's the time taken. That's what the question says. That the question says that, it takes the same time for both these objects to reach the ground, which means we can just equate it, right? I can find this t from here and then substitute it over here. So from here we get t squared equals so this is the value of t that we get over here. Now this we can substitute in the first equation. Okay. Now let's simplify this. Okay, this looks a little complicated, but it's actually pretty simple. So we'll say okay, so this is the final expression we're getting. So if you write this, you get h equals x plus y squared by 4x. And we see that that matches with option A, which means that option A is the correct answer. So here we have a multiple correct question, which obviously means that out of all the 4 options, there can be more than one correct option. Now, let's quickly write down what we know. So this is the information, and also the other extra information that's given to us is that when the bullet reaches the tip of the barrel, so let's say this, for just simplicity, let's say this is the barrel of the gun and the bullet is moving from here to here. Right? That's the tip of the barrel, and the question says that at this point A equals 0. Okay, now what do we do? Now the first option is saying that the bullet reaches the tip of the barrel at t equals 0.01 seconds, which means we have to find the time taken. So let's say it starts from here, we have to find the time taken for it to reach from here to here. Right? Now how will we do that? And what we know is that v is this much. How will we find this out? It is given that a is equal to 0 here, so the information is given in terms of a. So somehow if we get a relationship between acceleration and time, then that should help us out, right? Cool. So how do we do that? We know that v is this much, and we also know that a is equal to, or a, which is acceleration, is equal to dv by dt, correct? So if we just differentiate this equation, because v is given in terms of time, we should be able to find the acceleration. So a is equal to so this is the value of acceleration. Now what will be the, so to find out the time it takes to reach the tip of the barrel, we have to just substitute a equals 0, right? If a equals 0, the time taken will be equal to the time taken to reach the end of the barrel, right? Because the acceleration is 0 and the end. So let's just substitute that and see what we get. We get, if we write at a equals 0, the option says that the bullet reaches the tip of the barrel at t equals 0.01 seconds, which means that that's wrong. Option A is wrong, right? Now let's go to the next option. The next option says that speed at which the bullet leaves the barrel is 250 meters per second. So we have to check, or we have to find the speed with which the bullet leaves the barrel. How do we do that? We know that we know the velocity in terms of time, and we know the time it takes to reach the end of the barrel. That's what we calculated from here, right? So if we simply substitute this value over here in the initial value that we got, in the initial equation that we have, then that should give us the speed at that point, right? So let's see. So let's just write this out again. 250 meters per second. So the final answer we get is that V at that point equals 250 meters per second, which is correct. So our second option is correct. Now let's check for C. C says that the length of the barrel is below 1 meter. So we have to find the length of the barrel. How do we find the length of the barrel? We know this velocity, but what will help us find out a relationship between distance and time? Because the reason I need a relationship between distance and time over here is because we know that at a time of 0.005 seconds, the bullet reaches the end of the barrel, right? So how do we calculate the distance traveled? Simple. We can write V as ds by dt, right? Or dx by dt, however you like. So let me change it. So V Yeah, because if you apply the limits also, you'll get the same value because the lower limit is 0, right? So this is the value so we have a relationship between S and T. Now what we know is that T is equal to this value, right? Or 5 into 10 power minus 3. This value when the bullet reaches the barrel. So we substitute that over here. Cool. So the final answer we get is 5/6. Okay. Right. Now what does the option say? The option says that the length of the barrel is below 1 meter. Now 5/6 is obviously less than 1 meter, right? Correct. Let's check our units. Yes, our units are fine, so which means that it is less than 1 meter. So the third option is correct. Now let's go to the last option. At t equals 0.5 seconds, the magnitude of the acceleration of bullet is 9.9 into 10 power 5 meter per second squared. So simple. So we have to find where is a relationship between acceleration and time. So this is a relationship between acceleration and time, right? So I'll do it here itself. So the question is at t equals to 2.5. So let me substitute over here. The option says that the acceleration at that point is 9.9 magnitude of the acceleration. Over here you can see that the magnitude of the acceleration is 99. If I put magnitude into 10 power 5 meter per second squared, right? But whereas the option says that it's 9.9 into 10 power 5 meter per second squared, which means it's wrong. So the last option, B, is wrong. So finally, out of the 4 options, we have B and C correct. So over here we have a typical graph type of question, and this is a paragraph question, right? As you can see, this is the graph, all right? Now, what does the question say? The first one says, which of the following graphs correctly represents the position time graph according to the given situation? Okay, so you have to convert this into a position time graph. Now, how do you do it? Now, if you look at the options, you'll notice that there are no values over there. So we don't really have to worry about where the graph is changing and all that stuff. But what we need to worry about is what the graph will generally look like in terms of slope, etc. Now, since this is the velocity time graph, we have to make a position time graph of this. Right now, if, as you can see in the first case, right, let's say at this point, that is from 0 to 2 seconds. In that point, the velocity is increasing from 0 to 4 meters per second. So which means that the body is accelerating in the forward, in the positive x direction. So what will its displacement time graph look like? And we know this, right? Because the velocity, because it's accelerating and the velocity is moving forward, it will approximately, so if I draw it like this, it will approximately be a parabola like this, right? Because the slope is increasing. Now, if this is the xt graph, right, it will be a parabola, and it will be a parabola curving upward because the slope has to increase. Now, if you drop a tangent at this point and a tangent at this point, you'll note the tangent of these tangents basically represent the velocity, right? Because dx by dt equals the velocity. Now, because the velocity is increasing, the slope has to increase. So the tangent has to increase in slope. So therefore, it has to curve upward. Then, in the second part, you can see that over here, it's moving with a constant velocity. That is from 2 to 4 seconds. It's moving with a constant velocity, which means that its displacement should increase linearly, right? So therefore, it will be approximately somewhat like this. So if I remove this, graph will be somewhat like this, increasing linearly, okay? Now, in the third section, the section after the 4 second mark, from here to here, it's again, this time it's accelerating, but it's accelerating, or the velocity has a negative slope. You can see that the velocity is reducing in magnitude. Or it is accelerating, but it's accelerating by reducing velocity. Basically, you can say that the acceleration is negative, right? So how will you represent that? Well, in this case, it will be a parabola, but it will be like this. Do you see that? It will be parabola curving downward because the slope, if we draw the tangent over here, the slope has to reduce. Yeah, because the velocity is reducing. Cool. So this is approximately what if I have to draw it more clearly, say this. The graph will approximately look like this. It'll have a curving parabola like this, curving upward, a straight line, and then a curving parabola like this, which is curving downward, right? Now, among the options that we have, obviously, we can see that C and D are surely not right. We can immediately eliminate them just by looking at it, because there is no, there's no straight line that's curving up. There's no straight line with a positive slope. But if you look at A and B, they look similar, but there's a particular problem. If you look at B particularly, in the initial segment, the parabola is curving downward, which means that the graph looks like this. You see that? So, which means that in the initial segment, the slope is starting with a high value and then it's reducing, right? Which means that this graph suggests that the velocity should start with a high value and reduce. But that's not the case. We know that it's starting from a low value and then increasing, which means that B is also not the right answer. So the right answer obviously has to be A, which is closest to our prediction. So one point to note here is what's happening at this point. Now, if you look at the 6th second, you can notice that the velocity is becoming 0 and then it's becoming negative, right? So what does that mean? In terms of displacement, it means that the object is stopping and then it's changing direction, right? Because before 6 seconds, velocity is positive, and after 6 seconds, velocity is negative. So technically, if I had to show this, position time graph, so initially the velocity is increasing, so it will be like this. Then the velocity is constant. Now the velocity is decreasing. But at the 6th second, the slope will be 0. So if this is the 6th second over here, this is 6 seconds, you'll notice that the slope should be 0. And then it'll curve down like this. You see that basically the displacement is reducing now because the object is coming back. So if I had to draw the path, of this object, let's say this is the positive x direction, it would look like this. So from 0 to 2 seconds, it is accelerating in this direction, it's moving like this. Okay, and this holds, and then from 2 seconds onwards, it is still going in the same direction, but right now it's no longer. So from here, let's say this is the 2 second mark, right? Now from 2 to 4 seconds, it is still going in the same direction, but it is not accelerating, going with a constant velocity. Okay. Now from the 4 second mark, the object is now decelerating, or in other words, its velocity is reducing, but it's still going in the same direction because the velocity is positive. So from here to here, it will still go like this in the same direction, but the velocity is slowly reducing till the velocity reaches 0 at the 6 second mark. But then now you'll see that the velocity is changing direction, which means the body is coming back. It's reached 0, and now it's coming back like this for a period of 1 second, like that. So the body is like moving like this, hitting and then coming back. This is what it's doing. So at this point, at the 6 second mark, the velocity is 0, and that will be represented by the flat slope or the horizontal slope over here on the position time graph. So now let's go to the second question. What is the second question talking about? If you notice, it's saying it's only worried about what's happening between the 4 second and the 7 second mark. So from here to here, right? So the question wants us to compare the magnitude of the displacement, the magnitude of the distance, and the magnitude of the final position, right? Displacement, distance, and final position. How will we do that? Let's see. There are multiple ways to do this, but this is where, graphs help us, because if this graph was not there and all this information was given in terms of words, we would probably have to integrate and figure out the final position, final displacement, so on and so forth. But because we have this graph, it becomes very easy for us to calculate the distance and the displacement, because the area under the velocity time graph is the displacement, right? We know this. So let's see what we can do. Now in the first case, how would you calculate the magnitude of the displacement? What is the magnitude of the displacement? Okay, from 4 to 7 seconds. Basically, that will be the area under the graph from 4 to 7 seconds, right? Basically, if you take this, it will be this area and this area. Now, it's very easy to assume that we just have to add these two areas. That won't work because we are worried about displacement, not the distance. So what we need to do is calculate this area and then subtract it from the area below the graph, because that area will be negative, right? So if you talk about the area under the graph from 4 to 6, that area is half into base, which is 2, right, into height, which is 4. Right, so this is 4 meters. 4 meters, the area under the graph from 4 to 6. Now from 6 second to the 7 second, the area under the graph is half into 1 into 2, which is equal to 1 meter. Right, but this will be -1 because it's below the graph. Right, so we get 4 minus 1, which is 3. So the net displacement is positive 3. Right? This is the displacement in the between 4 seconds and 7 seconds. So the magnitude of the displacement will be 3. Simple. Right? Okay. Now what is the magnitude of the distance covered? Now the thing is, distance is basically again the area under the graph, but the negative displacements become positive. So basically, what's happening here is the body is moving like this and then it's coming back, right? So you have to calculate the distance covered from the 4th second to the 6th second and the distance covered from the 6th second to the 7th second, right? So the distance covered from the 4th second to 6th second is 4 meters, because that's the area under the graph. That's the area, that is this area basically, right? So that distance is 4 meters. And the distance covered from the 6th to the 7th is the magnitude of this area, because we're talking about distance right now, correct? So it won't be -1, but it'll be +1. So the net distance will be equal to 5 meters. Simple. Displacement magnitude is 3, distance is 5. Now what else do we know? We have to find the magnitude of the final position. How will you calculate the magnitude of the final position? Simple. We calculate the overall displacement throughout the graph. You basically add the areas under everything, include, and you subtract the area that's below the graph. So basically, what is the displacement travel in the first 2 seconds? That is from here to here. The displacement would be half into 2 into 4, right? Which is equal to 4 meters. That's the displacement travel from 0 to 2 seconds. Now from 2 to 4 seconds, that is from here to here, that will be the area under that graph. That will be 2 into 4 again, which is equal to 8 meters, positive 8 meters. So initially from 0 to 2, it's traveled 4 meters, and then from 2 to 4, it's traveling 8 meters. Okay. Now from 4 to 6, let's take this. Now that displacement will be half into 2 into 4 again, which is 4 meters. The distance, total distance traveled is 16, that is 16 meters, and its position is plus 16. So x is equal to plus 16. Okay. Now, what's happening if you look at the graph is that it is traveling backward, right? Because the velocity is negative. It's traveling backward. What is the distance traveled? Now that would be half into 1 into 2, which is equal to 1 meter. Right? So it's basically, its net position will be 16 minus 1 because it's traveling backward. So the position at the end of the last second, or at the end of the 7th second, will be plus 15. Right? So this is just one way of doing it. You can just calculate the net, that is the overall area. That is, you add all these areas. You add all these areas and then subtract the final area. That will also give you an answer. Another method will be to integrate, right? Because we know the velocity, we can calculate the displacement over here, displacement over here, displacement over here. That, in my opinion, is a much longer method. This way, using the graph and calculating the area in the graph is much faster, right? So finally, you get 15 meters. The final position is 15 meters. So let me write this down. The magnitude of the position is 15, which means that the ratios of these three values is 3:5:15, right? And the only option that matches that is option D. So option D is our correct answer.
For more videos and live lectures on the JEE, click on the subscribe button now.